So the next talk is by Dan Feldman, coresets for real-time tracking. Thank you. Go ahead.
Thank you also for inviting me here. Very excited to be here. I'll talk about the technique that I worked for the last at least 10 years, how I applied it and how it moved from theoretical computer science and computational geometry to more applied computer science and robotics. So we're still with defining a bit about, we're talking about real-time and big data. So big data, they usually talk about huge amount of data from many sensors on the fly, not offline from the floppy drive. And for this, we usually need streaming algorithms that use very little memory, not store all the memory. So it's not store all the data in memory. We want algorithms that will work in parallel without having to debug them as we usually do with parallel algorithms. So just use embarrassingly parallel algorithm. I mean, kind of totally independent. So we can run totally independent processes. We want simple computations. So we could use them with graphical processing units, which are very fast but can compute very simple operation, or even homomorphic encryption, which is what we're doing these days. And in the streaming, we don't want, unlike a lot of online algorithms, we don't want to assume things about the input of the order of the points. Formally, we said that we have infinite stream of vectors. This is the input, and it's just the number of vectors seen so far. The memory is just polylog n. And if you have m computers, for example, on the clouds or m CPUs, every new point, the running time should be polylog n, and should be faster. If we have 5 computers, it should be 5 times faster. Now, when we add also the real-time computation model to the story, this is not enough. We actually also need this value would not be just O of log n. It will be actually a few milliseconds. So in practice, it should be very fast. And another thing that we have a problem with the randomized algorithm. So if you have a quadcopter or a drone flying and do it with 50, which even with low probability, it will crash into the wall. Since you run it 30 times per second, it probably happen after a few seconds. So if the algorithm fails with some small probability, we're still in trouble. So we really prefer deterministic algorithms. Another issue is debugging randomized algorithm. It's really hard to know whether it is a bug in the problem or just one of the failure of the algorithm, because you have some probability of failure. I will discuss this a bit later. And the general idea behind coresets is that if you have large data or streaming data on the fly, and algorithm that you already have algorithm that we're happy with. So we find the model, we have an algorithm, and we're happy with the result. The only problem is that the running time is too slow, or the algorithm is just offline. So can we compress the data in some sense to a structure that we call coreset C, so that running the same algorithm on the coreset would get approximately the same result? So how we define, so approximately one proof that this will be 1 plus epsilon approximately, 1 plus epsilon approximation, the same up to 1 plus epsilon. So it's a multiplicative approximation. And we want also proof on the bound on the size of the compressions. We want to prove this, the trade-off, not just to show that we have heuristic for this. And intuitively, the basic idea, of course, is just to take some sample of the input, a weighted sample. So there are a lot of very nice properties of coresets. I have a lot of story, but I will try to just summarize in 1 minute. So first of all, we can solve optimization. We have provable guarantees on the trade-offs, unlike many other heuristics. Secondly, we have many NP-hard problems like k-means that are NP-hard, but if we just want to reduce the data, you can do this in linear time very fast. So compressing the data is significantly easier problem in some sense than solving the problem. The nice thing in practice is that we actually, after we compress the data, we just run the state-of-the-art heuristics on the compressed data. So that's how, when you want to improve a problem in computer vision or EEG or in robotics, we just take the favorite heuristics in the community. We just compute courses for this problem and run the heuristic millions of time on these courses and beat the state of the art using the state of the art. Or if you come into a company, instead of saying that you have an algorithm that is better than what all the engineers did all the last years with all the fitting to the customer, you just say, we just run your algorithm on my course, and that's how it will do better. So there is a lot of very nice. Also in the academy, it makes more sense instead of invent new algorithm for a community that does not know you, just to suggest courses for the famous problem that they already solve. I will explain how we can turn very slow offline algorithms into streaming algorithms, and also algorithms that work on the cloud in parallel processes. Very easy to implement. So the proofs sometimes are 100 pages of many Greek letters, state-of-the-art computational geometry, theoretical computer science, compressed sensing, but the algorithm is usually just 10 lines of MATLAB or Python code. And still the theory is very deep. These days we also apply it on the cloud, and the practical system that we use in the industry like Spark and Hadoop exactly fit to the model of Coreset of merge and reduce that again I will explain a bit later. The other thing is that there's no a single technique for Coreset construction. So it's not that I have a technique, I just apply it for different problems. It's a bit like approximation algorithms. We have some general techniques, but in general for every problem we need to have a different Coresets and algorithm. So that's why I still have a job and we have still many papers to write. Another practical thing is that a lot of companies tell me that they had great results using my Coresets for, I don't know, say k-means, and that's what they do with this Coreset. It turned out that they just run supported vector machine on the Coreset. It works great. So we don't understand why, but in practice, you can actually use one Coreset to solve other problems. So it also works very well in practice. So let's be a bit more precise of what exactly is the Coreset. So Coreset is a bit like God. No one knows exactly what it is. It can do anything if you can. They have the right definition, and the number of definitions are very similar to the number of papers about Coresets. The simplest definition is probably this. So you have some input set, points, lines, chair, whatever. This is P. And you have a set with query or hypothesis or models. Usually this is finite, this is size n, this is infinite. And we have some cost function. Sum of distance, sum of square distances for every subset of P to the query Q, which is positive or not negative. And now we say that we have this is epsilon, small number between 0 to 1, something like constant, not 1 over n. And we say that the subset of P is a coreset for P, or epsilon coreset for P, if for every query in this family, the cost from P to Q is approximated by cost of the coreset Q up to 1 plus minus epsilon approximation factor. So here I said this is a subset. In general, when you talk about sum, of course, we usually talk about multiplicative weights. Sometimes we need additive weights. Sometimes it's actually totally different structure, some expander or some strange other data structure, but essentially we usually want this property. And when we say that we can't find a coreset using the existing definition, we just invent another definition. The main idea that this will be small number of bits in memory in some sense.
Did you say, if you specify what kind of queries in Q?
Whatever you want. It's general framework.
So it's
P is a set and Q is a set, that's all we know. Still well defined, right? Because it's just a definition, I can do whatever I want. But yeah, in a few minutes we'll have to be more precise to actually do something that will work. So yeah.
Just want to get the quantification on this definition.
I give a lot of examples.
So you first fix epsilon and then you choose the coreset.
Yeah. So we have n points. You're going to give me tomorrow morning another query point, and you ask me what is the sum of square distances to the query point. So query is all the points in the world. The input is just n points. The cost of the subset to the query, or cost P to Q, is the sum of square distance for the input points to the query that will give me tomorrow. And the coreset is good if you can find a good subset, so that for every query that you'll give me tomorrow, I can solve the problem, approximate the cost just using C.
Yeah, I think the question really is, you have epsilon, then you pick C based on epsilon, right?
Yeah, so it's actually the coreset depend on epsilon and P. So it's kind of
And
Is it important that the cost of the coreset is the same function as the cost? I mean, could you, for instance,
No.
change the cost function?
Exactly. So essentially, that's what I did here, right? So in some sense, when I said C can be any structure, of course, also I mean that the cost function can be whatever you want. Actually, sometimes it turns out that can be very, as in compressed sensing, it's very easy to compress the data, but it's very hard to actually use this to solve the new optimization problem on the compressed data.
It sounds like your simple example about sum of square distances. If the coreset is small, then you need to multiply the cost by some scaling factor.
Yeah, usually the sum of weight is the same, is n. If we have n input points, you usually expect that the sum of weight of the coreset will also be n. Intuitively, that's what usually happens.
Subset, then you expect then the sum of squares is going to be much
Right.
smaller.
So this example more fit. Right. So that's for sum of square. We usually need this. This scenario is most for the farthest point. So if I should have given the example for take the farthest point, and then you don't need the weights. Given a query, just give me the farthest point from P, and then I won't give away. This is so the first coreset was about just subset because it's about covering. Then we have the more. So again, over there, I just talk with people from different fields. They describe me their problem, and we try to have a coreset for this problem. Sometimes it's just 5 minutes because we reduce the problem to an existing problem. Sometimes it takes a year or two. Most of the problem related to machine learning. Usually we do more and more robotics and more practical stuff that I will explain a bit later. The intuition why you have usually courses for machine learning problems is because in machine learning you usually have a lot of data and you look for a very simple structure, very few number of parameters. So in this sense, if you're just looking for a few number of parameters and you have a lot of amount of data, intuitively you don't need all the data. You can find a small compression. And this intuitively actually can formalize data using complexities measurement like visit dimension, for example. So let's start with few examples and then we get a bit more to the theoretical foundation. So for example, we have a paper with Fagin and Soken from Tel Aviv University about algorithm for cleaning noise, denoising image. So we have existing famous algorithm, but it works good only for low definition images and offline. And you want to apply it to high definition images. And also just said if you have a high definition image or just streaming, and you don't have time or you don't have space to actually run the algorithm on such data you get out of memory in MATLAB, just use uniform random sampling, or usually in computer vision they call it RANZAC, which is just a heuristic that says run the same algorithm on uniform sampling of the image and it will get the same structure from the image.
Could you stand to the side so that you're not...
Oh, sure.
So by uniform sampling, you mean sampling the pixels?
Yeah, let's see some examples. So you have a lot of points, and you just take uniform sampling. In this case, so actually, yeah, so in this case, you see, for example, the image in the left, you take uniform sampling. The problem is you probably take only green points and you miss all the structure of the woman. If you take uniform sampling for the Mickey Mouse down in this image, you probably just get white points. So the problem with uniform sampling, which is kind of the most popular coresets for engineers, is that you usually miss some points that you cannot get using uniform sample, but these points are maybe the terrorist, it's a fraud detection, it's the important pixels in the image. So it's not a good idea. And unlike uniform random sampling, which you can do in sublinear time, as Sonit usually, or people from property testing sometimes do, we actually allowed you to have linear time to actually scan all the points and carefully select the points for the coresets. So unlike property testing, you do have linear time to read all the data, but only one pass, you need to select the right points, and that's why you can solve more problems that, for example, property testing, which has more constraints, cannot solve. One other surprising thing is that actually, when we run the heuristics on the coresets, we usually get better results on the compression than the original set. So instead of 1 plus epsilon error, we get 1 minus epsilon. We don't have formal explanation, but intuitively what the engineers explain is that if you have some heuristics that find the closest local minima, with the coreset in some sense remove a lot of points, so the function is also much simpler. So when you find the nearest local minima, there's a better chance not get stuck in one of these. So intuitively, that's why we get actually better results on the coreset, because in some sense, the coreset also does some noise removal.
How do you solve this problem that random samples don't work?
Excuse me? So I'll talk how do you do the coreset, right?
For this specific thing, for the...
Yeah. So, okay, I will give a specific example for coreset for robotics. This is the million-dollar question, how you actually do this. This is the hard problem. Here, intuitively, you kind of sample you partition it into a small patch, so it's an original algorithm, and you sample the patch based on the variance. So if the mean is green and everything is green here, you take it with lower probability, but here you probably get higher probability. This is the bottom line of the paper. But usually it's a more complicated algorithm. So usually what we do is we define some non-uniform distribution over the input after one scan. And then we kind of sample points based on this new distribution. And we wait, so the importance is called sensitivity, which is the probability to sample the point, or to how important is this point. And the weight is 1 over sensitivity, so the expected value will be good. So we have a general theorem to compute coresets in general. So the first idea of using sensitivity was by Schulman and Langberg. And with Langberg, we generalized it to more general function set. Schulman and Langberg show it for k-means problem. So suppose that the cost is just the sum of distance, where distance is essentially just a positive function. I don't care exactly what it is. It does not have to be distance function, actually, any function. And we define the importance of a point to be the maximum of all the possible queries, the contribution of the point to the query divided by the sum of the contributions. So if you sample from this distribution, so for every point we have the importance of this point. And if you sample according to this distribution, and you can get a coreset, and as we defined in the previous slides, and the size of the coreset, the number of samples, is the VC dimension of Q, or something very related to VC dimension of the query set, divided by epsilon square, which is the error size, like in Chernoff-Hofting bounds. And this is the sum of all the sensitivities that you found. So I'll try to explain what's going on here. So this is always less than 1, because we have a value divided by sum of value. So you can always bound it by 1. So 1 is always an upper bound for this value. The problem is then the sum here will be n, because every point have one sensitivity, so we need to take n points, but we hope that the sum of sensitivities will be small. So in general, the way that the intuition behind this definition is suppose that you have a lot of points here and 1 point here. And you want, the query is just, say, 1 center. So why this point is important in some sense? Because there is a single query here, such that all the distance are 0 except this one. So this point have such query, such that this is almost 1. So it contributes to all the cost. On the other side, each one of these points, you cannot have such a query. So if you put the query here, it's smaller than all the others, and it's the same for wherever you put the query. So you cannot find for these points a center such that they dominate the cost. The cost is dominated by the specific point. And that is the intuition. So this is why this point is important. These points are not important. And again, the definition is very general for every definition for set P and Q. So why we still need to solve a problem? Because it's not clear at all how to bound this value. So it's kind of a reduction. Excuse me?
10 minutes.
10 minutes. Okay.
Should that summation be over P contained in C?
No. So you don't know P yet. So it's P of all the points. So you hope that not all the points are important. Really 10 minutes? Okay. So in general, we expect deterministic algorithms. So For example, when you use deterministic algorithms, we don't have this cold start that we have with sampling algorithms.
Sorry, no, I'm wrong. You have time until 4.
Right.
Oh, okay, sorry.
Quarter to 4.
Okay, good. Okay, so we want deterministic algorithms because, as explained before, we have when we're in robotics we have a problem with sometimes the algorithm fails because you run it thousands of times. Second thing, if you look for this is from one of the paper when you compare uniform sampling with non-uniform sampling and deterministic algorithms, you see that although in general in the infinity deterministic and the randomized algorithm are quite the same, when you take only very few number of samples, the deterministics take exactly the right samples, the deterministic algorithm. But the non-uniform algorithms, using all these concepts behind the Chernoff bounds and everything, is quite slow. And the intuition is, for example, so if you want to find the clusters in this set of points, and you just do uniform sampling, you will miss these points, which are very important. If you do non-uniform sampling, you still will sample this point. But as the coupon collector problem, it will take some time. You still take a lot of points here until you find all the points. In the deterministic algorithm, we just select this point at first, and only then start to select points from here. So you can actually get much, much better bounds on the theoretical bounds on the coreset size. So the first application. So originally, I designed algorithms with Micha Sharir and Amos Fiat in my PhD in Tel Aviv University for improving some problems in computational geometry. And then in Caltech, I worked with Leonard Schulman with the theory, but I started to work with people like Andreas Krauss on machine learning and more applied problems. And then in MIT, in my postdoc, I was the only one with a theoretical background. Everyone were engineer. So we started to apply to it for problems in robotics and real world applications. And one of the applications, for example, were iDiary. When we get GPS data from millions of people in China, and we want to have automatic summarization of what you're doing based on the GPS data. And so you can Google, for example, restaurants that I visited in a specific day and get the list. So you can Google your life, not just the web. And using Yelp, you can find out how much time you spent on each place. And the model that we use is that we have GPS data for a moving person. This is me in Cambridge. What you see in the graph there is that my XY over time, so we have a signal over time. This is just the map, the projection. And the main problem is that over time you see that even when I'm walking on the, or driving on the road, you see that there are a lot of noise that you want to smooth for segments. Much harder problem is to cluster all my visits from home to MIT, to cluster all these trajectories to a single trajectory to a single road.
So this is robotics?
No, the next slide will be robotics. So it's robotics lab of Daniel because we started with people and end up with robots.
Oh, okay.
So in a few slides, we do the same for track robots.
Okay.
So sorry, just to, you have a diary of a large number of people's movements, and you query what kind of queries can you launch here?
So I will just define it in the next slide. So what I'm actually interested in compressing the trajectory to know what the trajectory with small space. So what I do, so the optimization problem is that you have a lot of points, and you want to approximate it by a few linear segments for a piecewise linear function in some sense, which is a generalization of linear regression. So you want to partition the data into k intervals. So each interval will be approximated by a segment, and the fitting cost is the sum of square distance for each point to the projection of the corresponding intervals. And we want to solve it in real time for streaming data. So a coreset for this problem will be just a weighted subset of points, such that for every query, which is k segment in this case, the sum of square distance from the original points and the red points here will be approximately the same. And what happened in practice is this is one of the students moving, and you see that you collect a lot of points, but only few of the points get to our server. And in real time, we need to decide which point to send to the server. And one of the challenges is not only we want to compress the data, but we need to do it in real time and from streaming data. And maybe and later we had to do the same with video. So we have a lot of videos and we want to partition them into different scenes. And one of the main features these days for coresets in the context of big data and machine learning is a technique that's actually very well known in theoretical computer science called merge and reduce, I think for the 70s by Sachs and Barton. And it tells you the following thing. Suppose that you write a Python code or MATLAB code, a few lines that know how to compute a coreset of size 1/epsilon for a set of endpoints. The running time is turbo. It's offline on your laptop, non-parallel, non-streaming. The claim is that automatically you can turn it into a streaming algorithm, as I defined streaming in the first slides, and on the cloud, working in parallel on distributed data, using these tricks. So first of all, you take the small, say 2/epsilon points, and run your compression algorithm, so you get from 2/epsilon to 1/epsilon. The algorithm is slow, but since you run it only on a few number of points, it will be very fast. You do the same for the next chunk. Then you merge them, remove the original data, and compress this set. So we take the union of the two coresets and compress them again. Now, we can do this the same for the next set, and compress, and add and compress, add and compress. The problem is that the error will be larger. It will be 1+epsilon to the n. So we don't want to do this. Instead, we actually don't you take the union of this and the coreset there. We take the union of these two and compress them. And then we have kind of a binary tree. And in the morning, we have coreset for all the data. In every given moment, we have at most log n coreset as memory because each level has only a single coreset. And the only thing that we had to compute in every given moment is a coreset for 2/epsilon points. So the only thing, the algorithm always had to run on small number of points. And in the morning, we just run our heuristic or the exhaustive search algorithm on the small data.
But you need here epsilon to be less than a constant, right? Because it will still be raised to the power of log n.
Yeah, epsilon is less than 1. It's usually half or something. Or
Half won't be good, right?
so usually, 1+epsilon to the n for not so small epsilon is 1+epsilon log n. And epsilon is still constant, if I remember. I think epsilon less than some small constant still hold from calculus.
No, I don't understand. Like 1.1 to the log n.
Yeah, it should be less than 1. You're right. It can't be 2. But for
It has to be less than a constant.
less than constant, but not less than 1/n.
Yeah.
Yeah. There is an upper bound. Yeah, definitely. But epsilon again, it's not 1/n, but it's less than some constant. Again, in practice, we don't really have epsilon in the code. In practice, what we say, you have 200 points, return the best 100 points, and that's it. So this is just for the theory anyway. In the theory, you don't care about this constant when you review this paper. And in practice, it's just 200 to 100. And again, when we put epsilon equal 100, you usually get epsilon equal 0.001. And all the epsilon and delta, again, it's just from the theory. In practice, you just have 200 points and you want 100 points. That's all. So we don't worry too much about constants. So this is you see how the memory gets filled over time. It's really logarithmic as the theory promised us. All these jumps are because of the structure of the tree. So this is size of input, this is memory. And now if you want to run it in parallel, it's also very easy. So we can just send each coreset to a different computer and take the union and do this for each level. Or what might be better for infinite stream, if we have, for example, 2 computers, just give the even samples to one computer, the odd sample to the first computer. Each one will have its own tree. And again, in every second or in the morning, you can collect the root of these trees from each computer. And again, also notice that the communications is extremely small here because you just need to communicate the coreset and not all the data. Okay, so now to robotics. So in MIT labs, they use these huge, very expensive quadcopters with a lot of sensors. And you can only use them on the lab, on the special room in the lab, and you need to have a helmet because it's extremely dangerous. One of the students also cut his finger because of these guys. And I said, when I came to Israel, I said I really want to do, if I want to do practical thing, I want it really to be practical at home and not with masks. So the problem is not only the cost. This is a few thousands of dollars for such a robot. They are really very unsafe. They're illegal both in Israel and in the US. So instead, we have in the labs hundreds of these kind of robots. So you can just buy them on Amazon, $20 usually. The problem, they don't have really sensors on them. So we need to hack the protocol. But the good thing is that if you don't have a sensor, just some camera, you have a very nice theoretical problem that you can start to solve with not too many parameters. So this is some,
They don't have GPS.
Yeah, GPS denied. You don't have anything. You don't have also computer even, or then because they're so small. So I should have bought something, but it's more for the car, for the drones. Again, every student gets a drone to play with at home. If you go to the forest, you see a lot of them on the trees near the university, and it's very actually, if the I-1, the huge quadcopters crash in the wall, they're broken. This guy is just a piece of plastic, so actually it's very hard to break it when you just throw it on the wall, and also it's very easy to fix it. So it's really, really practical for research and for teaching. And again, the main challenge is to make it actually have to control it without sensor. So we have two approaches. The first approach to put some reflective markers on the quadcopters. So this is just like a markers with specific colors. So using infrared cameras, we detect these points and follow the drone. And we use for this a very popular system called motion capture system. We specifically use OptiTrack. This is a very expensive system, which sets infrared cameras that just track the object and tell you where it is. So, for example, they use it for games just to get the intuition of how it works. So you see they have all these markers on them, and they use it for, this is for a game for thing in Sony. So essentially, instead of having complicated animation, they just record the people. And where's my cursor? Yeah. So you see they essentially play the movie, and using the figures, they turn it into animation. But this system is really, really expensive, and we try to do the same thing with just a very simple. So each such camera that you saw them costs $6,000. Because all the algorithms are inside, it's really expensive hardware. The problem that we actually want a cheap system. So what we use is this Sony camera from PlayStation 3, just $5 on Amazon. And the idea is to have better algorithms. So the hardware is weaker, but the algorithm will be much stronger. So that's how we compete with the hardware. So we start to learn what algorithm actually this camera tries to solve. So this is the problem. So essentially, to know where you are, like if you look at the North Pole star, and you, based on the location of the star, you know where you are. So in general, the inputs is the endpoints, the end markers that you put on the robot or quadcopters, and in real time you see a specific set of points, and you try to understand what was the translation and rotation for the original set to the set that you see, to understand the new position orientation of the object. So if it's just translation, then it's easy. Then you know that the observed set is just the original set plus some translation vector. And it's very easy to compute this vector. But practically, you usually have a lot of noise, because the resolution of the cameras, you have few frames per second, you have delay until you get the image, and also communication problems. So you have some error, and actually this is not exact. So you have many. Okay. So we want to solve this optimization problem, minimize sum of square distance, for example, for each point to its corresponding point. So this, we want to find the vector t that will minimize sum of square distances from each point with the after translation to its corresponding point qi. And when you also have rotation, it means that not only the object moves, but it also rotates. And now the rotation is just qi, is just mean the original point multiplied by rotation matrix plus some translation vector. And now you want to, so it's rotation, translation. And now again, you want to find translation and rotation that will minimize the sum of square distance for the translated and rotated points to the observed points. And the main result is actually that I want to show now is that we can always find a small coreset, small subset of this point, so that if we solve the problem only on the small subset of this squared point, if you're talking about points in RD, we can get the same solution as if we have solved the problem on the original set. And the main idea is this. So to solve the optimization problem, it's very easy. You just compute the SVD. So P is the original set, N by D. Q is the observed set. You just compute the SVD. And these two matrices, two orthogonal matrices, the multiplication, give you the rotation matrix that you want. So the only problem that we need to compute this in real time. Another problem is that we usually don't know actually which point in the original data go to which point in the observed set. So not only want to minimize the sum of square distance, we also need from all the permutation of the point to decide which point should go to which observed point now, which makes things much, much harder. So, the way that we define coreset for this problem, for the post-estimation problem, is a weighted vector whose weight vector whose most entries are 0. And for every rotation matrix R and translation vector T, the sum of squared distance for the original point in the observation is the same as the weighted sum of just few small subset of this purple point. And in real time, instead of tracking all the points, we just track the coreset. And that's how we can solve all these hard problems, very hard problems, including the permutation problem in real time. So just give the main idea how we do essentially choose this coreset. So we essentially show that if you have the SVD, you just need to find a diagonal matrix with these indexes WI, such that the SVD of WP and WQ, which is the weighted set of points, will be the same as the original set, as the SVD of the original set. And then it's easy to see the optimal solution is essentially the same. So we essentially reduce the problem to the following problem. We have n vectors like this, and you just want to give approximation, fast approximation to the sum of these vectors. And again, as Stefan yesterday, we only have, we need that the algorithm will do very fast operation like matrix multiplication, and that's all. And this problem can be just solved using the Caratheodory Theorem, essentially. So if you have points, which is the mean of these points, you can always find a d plus 1 points that will give you the exact, so the convex combination of only 3 points will give you the exact point. And it works for general dimensional space. And when the d is very high, when we talk with computer vision usually, and we use a visual feature, which is very high dimensional space, we use an approximate version that asks that to find something that is very close to the mean, but use number of points that is independent of d, only on the error. And the algorithm is essentially you just pick a point, pick the farthest point. This is the first point in the coreset. Pick the farthest point for the mean, project the original mean on this linear combination, and continue. For the new mean, just take the farthest point, take the projection on this line, and the claim is that in every iteration, we get smaller and smaller error. So since I don't have too much time, I will try to show you some movie how it works in practice. So this is work with two of my students, Salome Nasser and Ibrahim Jubran. And so we just buy the robot from Amazon Cloud. We hack the protocol, so we can be so the algorithm can control the drone instead of if the remote control, like you see in the image. And next thing, this is the system. We just used 2 very cheap camera, 2 Internet of Things boards with just a Raspberry Pi, if you know it, is very small and cheap computers. We put the markers on the drones. And what we'll see in the next image is that we compare the system on the $1 million, this is the $1 million system in the lab. This is the weak cameras with our algorithm, with the Coreset, and this is using uniform random sampling. So we do a lot of repeated trials, and we actually see that using weak hardware but better algorithms, you can get very similar algorithms to the very expensive system with very weak algorithms. And later, we did the same with, instead of, to have actually autonomous drone without cameras around. So this is the random sampling. And the next thing is actually to have autonomous drone, we actually need visual feature without markers. For example, look for, localize yourself using points on the ground. So now instead of markers, we just have a visual feature on the robot, and we just track specific points that we find interesting on the image and compute coreset for this point. So now you don't have markers, you just visual feature from the algorithms that you find on the image. And this is shift features, it's called in computer vision, and the green point on the coresets. And we run the localization algorithm only on the new coreset in every moment. And there are many other.
What is this thing doing? What is it trying to do?
So in this case, just hovering. So if you solve the hovering problem, you're done. Because if you know how to hover, you can just send it to every given other point. So this is the main. If you solve this problem, we solve any other problem. And if you just use the same coreset over time, we see that it's become to be like uniform sampling. So actually, every 2 or 3 frames, we compute new coreset, because actually it takes more time than just 1 frame. So we keep tracking the same coreset for the next 2 frames, and then compute new coreset. That's how we deal with the real-time problem of commutation. There are many other open problems there. For example, we now try to find the problem with what happens when we have many quads. So in this case, you have kind of hard matching problem and clustering. So the existing system, we just try to cluster all these robots, but it confuse which point belong to which quadcopters. So we have beautiful clustering problems in real time that we had to solve.
Why is one of them banging it?
Because the camera loses it. I mean, when the camera confused, so if you don't talk with him for one millisecond, you just go like this. And again, when we talk about these guys from around Berkeley, the company that built this system, we actually talk with them about the algorithm. They really use very naive algorithms. So using our algorithm is very easy better algorithm, it's very easy to compete with them. It showed that they can do much better. And now they intend to actually implement our algorithm on their hardware, so to boost the running time, because now everything runs on the laptop, on the remote laptop, so it's extremely slow, and they use the embedded system, and everything is run on the camera itself. Okay, I'm running out of time, so we just converge. So what we're doing these days, so courses for deep learning is very popular until the buzz of deep learning will disappear. We will have courses for deep learning, we hope so. We're also working these days on courses for decision trees, more application for robotics. For example, what if you have GPS data and gyro data and maybe text data and other sensors, so how you combine these sensors, you have very interesting optimization problems there. Apple announced a few weeks ago that they're moving to differential privacy. So we have a paper about differential private coreset that shows surprisingly how compression and coreset related to privacy. And we want to have algorithm for higher dimensional spaces and for more problems. with Shafi Goldwasser and Daniela Ross, we now work to implement Coreset for homomorphic encryption. The idea is that it's extremely slow, but on the Coreset it will be much, much faster. So we have a chance, and especially if we have about 200 computers on the cloud, we show that you can actually solve machine learning problems using homomorphic encryption. And we also, again, a lot of people ask for implementation because it's very hard to read the papers, but it's very easy to read the code. So we now have try to have a general open library on Spark that implement all this Coreset, and we hope to publish it in next month. That's all I think. I'll be happy to talk with you about your problem, and maybe you can find Coreset for your problem. So feel free. That's how most of the paper started. Thank you very much.
Questions? Some quick questions.
What's the distance that you can use the cameras over? I mean, the drone, if it goes over 20 feet, 30 feet, you need to use the cheap cameras maybe.
Right. So the good news is that the very expensive cameras use better lens, so the distance is farther. But it turned out that it's better to have more eyes than stronger eyes. So if you have very many cheap cameras, it's much better than just two very strong cameras.
Single drone mount multiple cameras.
Yeah. So currently, what we have in all the building of the university, many of these cameras. The next step is, of course, to get rid of them and just put one camera on the drone. It's very hard because, again, we don't have computer on the drone, so we just use analog camera, but this will be the next step of the system, to just have one camera on the drone. But currently, we just spread many of these cameras. Again, they're extremely cheap, so we can use a lot of them.
Power will be okay for camera on the drone in power?
No, so this is another thing. We have, it's just about 10 minutes or something, but we have charging station. So we're just, after 5 minutes, you just replace with the other guy. And that's how we have 24 hours around the clock. And again, it's the students did this. I don't have it here, but just really simple piece of metal, and they just stand on it and replace between them. More questions? So that's it, I think. Thank you very much.